you have to rely on approximations instead. But it does improve performance in environments where you have long-term dependencies. Long short-term memory neural networks is another idea that I haven't quite been tried, but it's kind of a neural network which can store bits. So it would be cool to try an IC approximation based on this. The speed prior is Schmidt-Ober's suggestion for making Solomonov's distribution computable. It's still like double exponential computation time, so it's not really that efficient yet. Sort of the key component of this speed prior in Solomonov is, in a sense, compression. And there's actually a paper by Arthur at this AGI conference about making compression more efficient. So possibly this could also be a venue for making Solomonov induction more efficient. Yeah.
The granularity of your time slices, like how long they are, must be a critical factor, because if you go too fine, then you can't go into the task much.
Yeah, that's right.
So have you found some way of getting a sweet spot for that?
That's a good question. Yeah. I haven't thought much about that, but like, yeah, it's obviously a relevant aspect how to do that. Yeah. Right. Yep.
Why are you talking about Solomonov induction approximations? Probably it will be better to not approximate it, but make it more relevant to the reality.
Right.
Because, for example, Levin complexity doesn't approximate Kolmogorov complexity. Well, you can say that Levin complexity approximates the Kolmogorov complexity, but for my point of view, it's more relevant to the reality, because it's much less probable to observe data from sources which require more time to produce the data. So in this sense, is it good to talk about approximations? Probably we need not approximations, but more adequate statement of the problem.
Yeah, like that's obviously the idea, right? If you can be more efficient and more tuned to the real world, that would be really good. And as you say, Levin complexity is probably a step in this direction. But it's probably still too slow to be practically useful without further adaptations. Yeah. So let me also say something about feature reinforcement learning. So not that much time. So we have this agent and it sees these histories. And this is the same for humans, right? We take actions and we actually just get a sequence of percepts, but somehow we manage to infer states of the world. Like we generally think like, I'm at home, I'm at work, I'm tired. Like we tend to think about the world in states and plan from states. So it's a natural idea to try to get agents to do the same thing, even though it only sees a history. So feature reinforcement learning is this idea that we should find a map file that maps histories to states. Yeah, this is just some examples where state representations are valid. I think in most environments there is some kind of state that generates history. Right. So when we're using like a robot with like some standard RL and NDP application, then as designers we tell the agent this kind of percept means this kind of state. Perhaps a GPS signal or something like that. And the feature reinforcement learning approach or the PhiMDP approach, so we should let the agent infer this map from histories to states automatically. So feature reinforcement learning, you could say it's an alternative to partial observable MVPs and to predictive state representations. Basically what happens is that the environment generates a percept. This is included in the history. The agent searches for a map phi that takes histories to states and tries to minimize some cost of this phi. Basically, how well does this phi predict the history? Or like the states generated by this phi, mapped by this phi, how well do they explain the history? And once you have this map phi, then you know what state you've been in, or at least think you've been in, and then you can use sort of standard MDP techniques, standard reinforcement learning techniques on this inferred state representation, and do all the learning and planning on those, and take an action based on that. It's a general idea. There's been quite a few works on this approach. It's like some theoretical results on asymptotic consistency on this inference technique. And then various like approximation, like it's obviously computationally hard to find the optimal map from histories to states, but in small toy problems this can be done. Otherwise, you typically have to rely on some kind of modifiable techniques, for example, simulated annealing, so search this space of possible maps, you find some local minima. It's also possible to use a variant of the context tree weighting algorithm and to use context trees for states. That is called context tree maximization. The math works out similarly, so you get like similar good performance, like this constant time algorithm, which is nice. And the experimental performance is similar to the MCX-CW approach. Similar extensions, looking for context trees or looking socket trees applies here as well. Have structured MDPs, so instead of trying to infer a discrete number of states, you try to infer some feature vectors. For example, how bright is it? What's the temperature? If you know a vector of features like that. There's also been some theoretical work on relaxing the Markov property for this state. It's called extreme state aggregation. You can find much more in the references. Finally, I just want to mention the model-free ICT approach. So, model-free methods, both of the previous approaches, both feature reinforcement learning and MCX-CW, they try to find some model of the environment and then plan from that model and find the best action. What has been found in reinforcement learning is that model-free approaches are often much more efficient. So for example, I'm sure you've heard about Q-learning and SARSA. These methods actually don't really build a model of the environment. They just infer how good is this policy or how good is this action in this state. So they try to sort of learn the value function, the expected return from an action by induction. And this means you don't have to do any planning. Because if you manage to infer the optimal value function, then you can always act optimally with respect to this value function. There's been some work on this, and in particular by Buju Vanessa again, a model-free version of IXC learns to play Atari games, and this time actually watching the screen, sort of similar to what PQN does. So it's a pretty impressive performance in this approach, but doesn't really explore that much yet. I'm basically out of time, so I'm just going to skip ahead to my conclusion slide. You should ask me about all the other cool things. Right. So, universal artificial intelligence, or XD, sort of foundational theory for AI. It answers the question, what is the right thing to do? And the answer is in form of this one-line equation It's useful for inspiring practical agents, also for predicting and controlling super intelligent agents. I'm very sad I didn't get to speak about that, but I'll speak more about that in my talks later in the conference. And identifying and addressing fundamental challenges like notions of optimality and exploration versus exploitation. Thank you. Any questions? Otherwise, appreciate it. Yeah.
Regarding the short discussion about right reward function to how would you compare, for instance, self-preserving agent to the IC formulation and of course the original cybernetics formulation of autonomous agents?
Right. Yeah, IC isn't really self-aware in that sense. It's sort of a dualistic framework.
I said, for instance, self-preserving agent. You know, the
Are you filming?
well, the agent
Are you filming?
that wants to minimize surprise.
Somebody might be.
Minimize surprise.
Yeah, it turns out that's equivalent to Bayesian prediction.
Oh,
Yeah.
I don't know
So
about that.
that's the best theory of autonomous behavior that I know. So that's why I thought, I mean, it would be nice to compare. I'm actually writing a paper on this, so I was curious what you are thinking.
Let's discuss it more. I haven't
Yeah,
thought about it.
so let's think it offline.
Yep. Yeah. Anyway, let's talk it out. Please.
Well, sitting down and watching on the wall will minimize